coming. Things are really starting to shape up on Cerro Armazones, where the ELT is being built, with the building starting to look like something that can hold a giant telescope. And that means that the first generation of instruments are also being designed and built. So today we have a very special talk from Pello to tell us about one of those instruments, the multi-object spectrograph MOSAIC. Her career has taken her from Barcelona to Toulouse, to Paris, and then to Marseille, where she became the first, and I think the only, female PI of one of the ELT instruments. And if I tell you how many people told me today that they're excited to hear your talk, you'll be very happy. So we're very happy to have you here. Thank you very much for that.
Thank you very much. Well, before starting, I would like to thank you all to be here today for inviting me for this talk, because I am going to talk about this instrument that for me is a great instrument. And I am particularly happy to see around the audience so many young people, young astronomers, that will be for sure the astronomers that will use the facilities of the ELT in the future. And really I'm happy to present this instrument to you, because I think that it is done to fulfill a lot of your needs in the coming years. So let's start. Okay, first of all, I'm going to give this talk, but I'm not the only one working on the project. We are 350 people, roughly speaking. I'm going to show a lot of material, of course, coming from this collaboration, this large collaboration. So I'm giving this talk on behalf of the consortium, on behalf of my colleagues. So I have just cited here people providing the majority of the material I'm going to use together with my own material. So I would like to thank them a lot. So here is the outline of my talk. I'm going to be talking about MOSAIC, the concept of MOSAIC, for about 1/3 of my time. I'm going to describe the project status, and then I will move to the MOSAIC science cases. I think you will be more interested about this, what the collaboration foresees as hot topics in science with MOSAIC. And I expect to keep a few minutes at the end for an open discussion if you want to know more about this instrument and the developments. It is good to remember that, as it was said before, the ELT is no longer a dream. The ELT is taking shape. Please look at this image. This image was taken end of August this year. This represents a view of the sunrise behind the dome of the ELT, as seen from Paranal, about 23 kilometers away. And as you can see all the structure here, the workshops, etc. And you see that essentially the dome is already visible. And if you look at the aspect of this dome about 1 month after that, you see here a much better view in the daytime with all these people here that were all the very well-known people coming for the I think it was the first official inauguration, I think is the word, for this ELT taking shape. Okay, so according to ELT people, 50% of the total work has been done. Okay, so this means that it's coming. It's not just something that in the future will happen. It's really happening, and we will have it very soon. So this is what motivates my talk. I'm going to talk about MOSAIC very shortly. What's the concept of MOSAIC? MOSAIC is a first generation instrument. It is not a first light, so the words are important here. Some instrument will come before for the first light, and this instrument is coming for the first generation, okay? Immediately after that. MOSAIC is a versatile multi-object spectrograph that is going to be located in one of the Nasmith platforms of the ELT. This instrument has been, let's say, being modified over years, during about 10 years, and you have some ancestors before MOSAIC arrived, playing about this concept of what is the best possible multi-object spectrograph for the ELT, okay? So now we are convinced that MOSAIC is actually the answer to this question. MOSAIC is going to cover a very wide wavelength range, as you can see here, between 3,900 Armstrongs and up to 1.8 microns, so the complete H band in the near infrared. And the main characteristic is that MOSAIC is intended to use the widest possible field of view provided by the ELT. This is about 40 square arcminutes, okay? The maximum that can be accessed. The first light instruments only use the very center of the focal plane. We use, as much as possible, the focal plane to cover this focal plane completely with as much as possible fibers, because this is a fiber instrument, providing us this multi-object capability. We will have essentially two observing modes, the MOS mode, high multiplex mode if you prefer, and also a multi-IFU with 8 small IFUs that can be located across the field of view. This is how MOSAIC will look like in the Nasmith platform. You have this artist view here on the right-hand side. Just to give you an idea, this is a huge volume and a huge mass. If you take the size of this complete instrument, it is about 7 by 7 by 10, meaning that you can easily put my entire house inside this volume. Now we are working to see how we can reduce a little bit the volume, so the design has been changed a little bit, because we are in a phase working towards the PDR, and we are going towards the final architecture of the instrument. So trying to simplify as much as possible while keeping the high-level requirements and gaining as much as possible in terms of volume and mass to fit in the Nasmith platform. So essentially what you see here is the front-end system here collecting the light from the telescope beam. And this is a very complex system with many subsystems here, sending the light towards two different spectrographs, the near-infrared spectrographs and the visible spectrographs. On the left-hand side, you have a view of the focal plane as you can see it looking at the front of this focal plane. And you see essentially the surface covered by the useful science field that is going to be about 7.5 arcminutes in diameter. And all the MOSAIC modes will be assisted by ground layer adaptive optics using both natural stars and also laser guide stars. So this is quite usual. And because we want to have the best possible image quality. When presenting the science, you will see. Well, I'm going to show this in a minute about the field of view. Actually, they are not fibers, but fiber bundles, okay? And we try to maximize, to improve as much as possible the PSF on the focal plane. So possibly this illustrates a little bit better my purpose. So what you have here is the ELT is not a telecentric telescope, so we have to really follow the shape of this focal plane using a tiled and stepped design in such a way that we can put all these fibers and all these fiber positioners the right place in this focal plane. Of course, it is a little bit exaggerated when you see the scale, huh? Okay, but this is to give you an idea about what I'm talking about. So here again, you have this famous field of view, 7.5 arcminutes or so. You have the laser guiding stars, and you have this series of positioners that combine together visible and near-infrared fibers in such a way that you can combine together different observing modes. For instance, you can perfectly well locate some of the fibers on the visible fibers on the field and have a staired exposure, and then another exposure with the near-infrared fibers. So this optimizes, of course, the speed of the survey for surveys, and this is going to be very versatile. As an astronomer, I think that this is enough to understand the point. So you have, presently, this is the current design. We are modifying this a little bit, but I'm not going to talk about this too much. You have on the top of the field of view, at the same time, visible and near-infrared fibers. Actually, these are not fibers, but fiber bundles, as you can see here in this design. And you have a high multiplex mode in the visible and in the near-infrared. And you have here the typical size of these two fiber bundles to answer the question. So a little bit larger in the visible than in the near-infrared. And then, in addition to this, you can put these 8 mini IFUs distributed in the field and this facility is only available in the near infrared. So this is the choice that has been made for this instrument. Going more in depth about the characteristics of MOSAIC, here are the 6 different observing modes that we will have, some of them simultaneously, as I said. So you will have a multi-IFU mode in the visible, multi-IFU mode in the near infrared, and in both cases you have the choice between low and high resolution. Low resolution here means at least 4,000, close to 5,000 as well, and depending on where you look at precisely. And high resolution means, at the moment, 18,000. And then you have this multi-IFU mode, only in the near infrared, that has also low resolution and high resolution mode. Possibly, this table will illustrate much better and quantify what I just said in terms of what are the top-level requirements for this instrument, both in the visible, in the near infrared, and in the multi-IFU in the near infrared, in the low and high resolution modes for each one of them. Okay? And here you see the multiplex capability that is at least 140, I should say. It will be 200 in the near infrared for sure now. We have 8 multi-IFUs, and here are the wavelength domains for each one of the modes in the low resolution and high resolution modes. Of course, in the high resolution mode, we select selected windows in the spectra in such a way that we cover the needs of the stellar astrophysics, knowing that this is the main use of MOSAIC for these high resolution modes. Well, the resolution I already commented on that, and these are the apertures that we are using now. As you can see, the mini IFUs are relatively small, but they are enough for the science needs, the science cases. Okay. Now, why I said that this is a unique instrument? Well, it's easy to understand if you locate MOSAIC and MOSAIC capabilities on the top of a couple of diagrams that compares the capabilities of MOSAIC with the other ELT instruments. Let me just show you this diagram here. This is taken from the ESO site. It's not something that I have idealized, where you show, you can see the spectroscopic resolving power as a function of wavelength. You have here in different color codes all the first light instruments that will be available at the ELT. And MOSAIC actually occupies this region here in dark blue. Used to be dark blue. I don't know how the projection looks like, but used to be dark blue. And as you can see, it will be a quite unique facility covering the blue part of the spectrum, electromagnetic spectrum, with a high resolution or large resolution capabilities. So this is relatively unique as compared to the other instruments. Of course, MOSAIC has no imaging mode. It's only a spectrograph. And the other diagram I want to show is this one showing in the same landscape the spatial resolution as a function of the field of view. You will not be surprised to see that MOSAIC is located in the top corner here on the right-hand side, covering the maximum field of view with a very good spatial resolution in any case. So in this respect, it is quite unique, as you can see, as compared to the other instruments in the landscape of the ELT. So these are the 2 reasons why I'm saying that the MOSAIC is quite unique. It's quite unique because of the multiplex capability, spectral resolution, wavelength coverage, and the large field of view that can be accessed for most multi-object observations. Needless to say that MOSAIC is optimized to provide a high survey speed and a high surface brightness sensitivity for faint sources, because this is the main science cases that we want to address with MOSAIC are the ones related to the very faint objects in the distant or local universe. To do a kind of science that nobody else can do apart from MOSAIC. So this is why I put here this sentence, is that MOSAIC will be a follow-up machine for all the space missions and ground-based experiments that you know possibly or you are participated on, like, for instance, JWST, launched last year, Euclid, launched recently, Rubin, Roman, SKA, and also Athena or other facilities coming in the early 30s. Okay, this is the idea. It will be really a quite unique instrument. Possibly, I'm going to come back about this in the next slides, but this is just to show you how this translates in terms of the limiting magnitude for MOSAIC as compared to other facilities that you all know. In this case, regarding the limiting magnitude for the continuum in a way to we reach a signal-to-noise of 10. Of course, here I'm using a very long exposure time. We are using a long exposure time that is about 40 hours. This is the maximum that you can expect reasonably with an instrument of this kind. As you see that we can reach as deep as 27 magnitudes in the continuum in this wavelength domain, you can see here in orange, as compared to the capabilities of other facilities like the JWST, for instance, force at the VLT for the continuum. You can see the difference is quite dramatic. And you can see as well that for high redshift galaxies, represented here by these blue signs in the res frame UV and the different lines that you can catch with the JWST, we will be able to provide UV res frame follow-up for this kind of objects, providing quite unique science for these extremely distant galaxies. Well, now let's move very quickly through the project status, where we are in this adventure. Well, MOSAIC has been reorganized recently, and we are now in the B1 phase. We had the kickoff meeting in March this year in Paris, and we have just signed this summer officially, but we started earlier, of course, the B1 phase agreement with ESO that will take us to the SAR. This is the System Architecture Review. That is the first big review that we have to pass with this design. And we expect to start after this the B2 phase up to the PDR, the Preliminary Design Review, that will take place between 25 and 26 for the different parts of the instrument. I'm not going to enter into the details about how we are organized. I'm just giving the main lines. MOSAIC is a big consortium. You can see here we have 24 institutional partners and 31 laboratories spread around a lot of countries. And we are more than 350 members when you count everybody. A very important point here is that the consortium is responsible for raising and complete the construction and raising the funding and the resources to do that, contrary to other instruments. And of course, this has a big impact in our work. This is a summary of what we have been doing. So you have here different progress meetings that took place this year. The instrument is progressing very well. And as I said, we expect to have the SAR next year in September, the PDR end of 25, the primary acceptance in Europe in 31, and the first scientific line in 33. This is a very ambitious and aggressive schedule, I can tell you, okay? But this is how we foresee to progress. For different reasons I can develop if you are interested later on. The organization of MOSAIC is a very classical one. I'm not going to read what is there. We have a classical organization with a PI, co-PI, project office, with different members here, MOSAIC board made by all the partners, and also an institutional board with all the paying agencies, etc. So this is a very classical configuration. We have also a science team, a very powerful science team with different people in charge of the different science working groups that are participating in this phase to the development of the science cases. The project is organized around what we call channels. What is a channel is a piece of the instrument, front-end visible channel, near-infrared channel, and the GLAW channel in charge of different countries. You can see here, France is in charge of the front end, Netherlands is in charge of the visible channel, Spain of the near-infrared channel, and UK of the GLAW channel. And all these channels actually are developed separately, but in a coordinated way to build the full instrument with an instrument level channel here, where we have all the usual control, software, detectors, etc., that are in fact transverse aspects or work packages with respect to the full instrument. One slide to talk about the cost. The cost of the instrument, only one slide. It's estimated to be around 51 mega euros in terms of the hardware. We have this amount of money distributed mainly on the two spectrographs. You will not be surprised. And also the detectors, in particular the near-infrared detectors that are quite expensive. And of course, we have also a lot of FTEs. We have more than 750 FTEs, the full-time equivalent, meaning that the cost of the instrument in terms of total resources is very high. And of course, we will be rewarded for this. We will have at least 65 nights for the FTEs. This is a lower limit, and a number to be defined of nights for the hardware. And we expect to have about the same number. So this means that we will have more than 130, roughly speaking, of GTO nights with the ELT for the construction of the instrument. And all the GTO will be used to be shared among the participants to execute what we call MOSAIC surveys around the science cases that I am going to talk about in a minute. Okay? So this was my last, let's say, management slide. Now let's go to the science cases. We have identified 6 science cases corresponding to 6 science working groups that look like this. We have a science working group number 1 about the first light and reionization. Science working group number 2 about the inventory of matter in the universe. Number 3 about the mass assembly of galaxies through cosmic time. Number 4 and 5 respectively dealing with the resolved stellar populations beyond the local group and galaxy archaeology. I think that some of you are interested in all these topics I just mentioned, together with the very last one, the new one, which is about the transients, Science Working Group 6, which is the last science working group developed, and it's relatively new with not so large number of people. Here you have some numbers to illustrate how many people is participating today into these 6 science working groups. As you can see, you have a lot of people belonging to 14 countries, sometimes with multiple affiliations that justifies the fact that we have only 252 full members. And science working groups 1 and 3 have a large number of members, together with science working group 4 and 5. The 3 of them interest a lot of people. You will not be surprised because of the large number as well of the science cases that can be developed within these working groups. Well, now I'm going to spend a little bit of time talking about the hot topics within these science working groups, science cases that can be addressed by MOSAIC, and why MOSAIC will be interesting. I apologize in advance because, of course, I am biased. I am biased towards my own topics, of course, and of course, I cannot be an expert on everything. Some of you know better than me, or can already imagine with what I just said, what you will do with MOSAIC, okay? But let me just put things clear and summarize what we think will be interesting to do with MOSAIC. I'm going to start in the disorder. I'm starting with the local universe, stellar populations in the local universe. So the first big topic is about the stellar population beyond the local group. In this case, what we want to do is to explore the star formation and the chemical enrichment histories beyond the limitation of the present-day instruments, or beyond the local group. Today, with the classical telescopes we have, like the VLT, for instance, 8 to 10 meter telescopes, the maximum we can reach for the study of stars in this local universe is typically the red giant branch at the distance of the Magellanic Clouds, typically. So what we want to do with MOSAIC is to address the diagnostics based on several features that will be in the high resolution modes of MOSAIC, like the calcium triplet or a magnesium B triplet or the G band, etc. And this will be extremely useful provided that we can cover this blue side of the spectrum, and this is actually true. We have already secured that we can go as blue as possible with MOSAIC. And of course, with the highest resolutions possible to do so. And apparently, we can accept low resolution provided that we have a very large signal-to-noise. So this will be a compromise to find a trade-off between signal-to-noise, okay, and resolution to see what's the best configuration of MOSAIC for your science. Apparently, a resolution of 28,000 is enough for the measurement of interesting species. And, well, so apparently it's enough. We don't need more. And we can gain also in terms of signal-to-noise without increasing the spectral resolution much with respect to this 18,000. Here you have a graph already published a long time ago, and the present MOSAIC started to be considered, representing the signal-to-noise that you can reach as a function of the V magnitude for galaxies in different distances here, to give you an idea about the high signal-to-noise above or the order of 50 that you can reach, even for relatively faint stars, as you can see here, allowing you essentially to observe mid to late O-type dwarf stars out to 3 megaparsecs, and of course bright giant supergiants a little bit far away. So this is very important because this will allow the group, the science working group, to observe these stars, massive stars, in a wide range of galaxies, and understand really the environment of stellar evolution, in particular low metallicity. So this is a very hot topic here in the MOSAIC science working group. Another very important topic is galaxy archaeology. In this case, what we want to do is to constrain the star formation for very metal-poor environments by analyzing the metallicity distribution of the stellar population. And the targets will be stellar heroes in the bulge, and also dwarf spheroidals and ultra-diffuse dwarfs in the local group, within the local group. Just to illustrate this is not my topic, but I think this example is very illustrative. Here you have in this example one of these dwarf galaxies in the local universe, the Draco 2 galaxy. And as you can see here on the left-hand side, this is an image of this galaxy showing the bright stars. Okay, this is to show the extent, the field of view that is particularly well suited for MOSAIC. Remember that MOSAIC will have 7.5 arcmin² side, so this is particularly well suited for this kind of study. And you can reach with high resolution observations measurements on these dwarf stars in this kind of galaxy. So this means a major improvement with respect to what is currently available with 8-meter telescope. And of course, we also need this high resolution mode to make progress with high signal-to-noise. So then there is a trade-off to find between distance, of course, and resolution. Another comment I will make here regarding galaxy archaeology is that this is going to be highly complementary with other facilities like Harmony, that is going to be very efficient to observe the core of this kind of objects, and MOONS, that will have a high sensitivity and observe a large number of galaxies, or large target density. But MOSAIC will be precisely what it provides a bridge between this core and the extended field with high spectral resolution to measure the chemical abundances in globular clusters, for instance, in the inner galaxy. As you can see here, this is a relic globular cluster in the bulge. So you can see this kind of object that we expect to observe. One slide to show something interesting about the transients and multi-messenger astronomy. This is just to remember that this particular science case is not driving the architecture of the instrument. This is going to take benefit from the instrument as it will be, knowing that in the 30s you will have a large number of facilities for multi-messenger astronomy. And in this case, you will have plenty of events that will be observed located by other facilities. And MOSAIC will provide, in this case, the electromagnetic counterpart detected beyond the local universe, thanks to this capability of collecting photons. So, of course, we expect thousands of events measured by these coming facilities, and so multi-messenger observations will be of capital importance to reach the comprehension of the universe, to work to really understand the electromagnetic counterparts. So, in this case, what counts here is the large field of view, the high multiplex capability to target different objects in the surroundings, so the environment of these objects, and of course to observe very faint transients. That is not possible without such a big capability of collecting photons. Well, in this case, of course, the targets will be selected from other facilities in the optical to radio facilities like the Rubin Observatory of OSKE. Well, I'm not going to say more about that. This is a very new science case, and of course, if you want to participate, you are more than welcome. So let me now concentrate a little bit more on the more distant universe, starting with the science case number 1. Here, I admit it, I am biased, okay? So what are the big questions here in the distant universe? About first galaxies and the epoch of the reionization, knowing that the James Webb is doing a lot of things already. So the idea is to be completely in synergy with the James Webb and work on observation that can really provide more than just an incremental value, okay, to what James Webb is doing. And one of the questions that we still have is to know about the sources of the reionization, their properties, and in particular how the different kinds of ionizing sources intersect together in a given volume of the universe. And this is not an easy question to answer because observations have strong biases because the observational selection actually completely determines what are your results very, very often. So it's very difficult to really understand what is reionizing the universe in a given volume. Ideally, we want to have to observe all the star-forming galaxies in the same volume of the universe with a well-controlled selection function. This is very difficult to do today with the current facilities. And also, we know there is a rapid evolution of the global properties of these galaxies as they are observed today, in particular, for instance, for Lyman breaks, but also for Lyman alphas, etc. I'm going to show this in a minute. So this is based on the separated study of the different kinds of sources. For instance, for the Lyman breaks or for the Lyman alphas. And also, we all agree today in that apparently the reionization is dominated by faint star-forming galaxies. So these faint star-forming galaxies are currently today beyond the capabilities of the telescopes to observe them directly unless you have gravitational lensing, strong cases of a strong gravitational lensing that facilitates your life. So the progress is relatively slow in this area, okay? We have some recent publications that are very nice, but still show this limitation. For instance, you have here a study published in the 2022, I have taken the last one, showing the evolution of the luminosity function here as a function of redshift, showing that when you go from low to high redshift, essentially the normalization changes a lot and the slope becomes more and more steep, okay? So this is something that everybody knows and accepts today. This is a combination of many previous observations. And of course, you have also an evolution of the normalization here, very clear. And well, that's fine, that's nice, but this result is based mainly on photometric samples, okay, with all the limitations that it has, because you don't have spectroscopic confirmation, and you can have many kinds of, biases and here that prevents you from obtaining photometric physical properties only using photometry, okay? You need spectroscopy really to make progress. Same thing here when you look at what you obtain, when you look at the Lyman alpha emitters, behind lensing clusters, so you're pushing as much as possible your detection of Lyman alpha emitters. They are very faint, as you can see here. You have different beams for the luminosity function. This is based on Muse data. Nice. You can select all the Lyman alpha emitters in the cube between redshift around 3 and 7, limited by the wavelength domain of Muse. And in this wavelength domain, you still see some evolution in the properties of this luminosity function. And at high redshift, something that still looks like a turnover of something that is actually expected. But it's very difficult to do better than that. Okay? Even with a lensing cluster, you still struggle to have spectra of good quality here in this domain in order to understand how these galaxies look like really. And you can also suspect sometimes that the strong lensing puts some biases into this exercise, even though it's not necessarily the case. Same thing when you look, okay, if you want to compute the ionizing power of these guys, you have to count how many you have in the volume, right? So people used to work on the prevalence of Lyman alpha emission among the Lyman break galaxies. This is the diagram here, one of the last I have found. And usually people with a large dispersion, you can see this, depending on how you count your Lyman alpha emitters among the Lyman break galaxies, you can end up with many, kinds of biases here, dealing with, for instance, different locations of the Lyman alpha emission with respect to the stellar emission, etc. So you have a maximum here around redshift 5.56, and then it goes down, and we understand that this is possibly due to the fact that you have more neutral hydrogen, also Lyman alpha is not escaping so easily. And of course, if you start to count, to consider together the, let's say, the star formation rate that you expect from Lyman alpha emitters, Lyman break galaxies, identified separately, you still see some biases, some trends, very well known. For instance, here it is observed for the very faint galaxies that seems to be to have escape fraction, let's say, Lyman alpha photons escape more easily than UV photons for these very faint galaxies, for instance, in this diagram, but it's not, this is something that is full of systematics, okay? We really struggle making progress in this kind of analysis, and this is done with, again, lensing clusters, okay? So this is the maximum we can do with 8-meter telescopes, I'm very sorry. So if you want to really to understand this, this intersection, how these galaxies look like as a full population, you need to do better than that. So this takes me to this diagram, here, this example, and a list of what we know about high-energy galaxies from 10-meter telescopes and the problems. So usually galaxies at redshift more than 7 do not show, it is impossible or very difficult to measure the continuum with 10-meter telescopes. Okay, so we need more photons and a larger capability. On the other side, I already mentioned significant increase on the fraction of galaxies with Lyman alpha emission when you go to redshift 6 or so, and then going down. The detection of metallic lines in the UV res frame that are needed to estimate the Lyman continuum escape fraction are not easy to detect. To detect them, the only thing you can do is to stack together a lot of spectra or use gravitational lensing, and this is currently the only way to go. So for instance, you have here an example of 31 objects stacked together, the equivalent of 52 hours of exposure time, redshift around 6, and total magnitude in this combination about 26. And this gives you some absorption features that are useful for this exercise, okay? But this is, of course, the maximum you can do, again, with an 8-10-meter telescope. If you want to do better, forget it. And this is what MOSAIC is done for. Okay, so if you want to characterize the first galaxies that are responsible for the reionization in a complementary way with James Webb, there are different things you can do. The first one is just try to detect the Lyman alpha line. And this will be indeed possible, as you can see in this simulation of a galaxy of magnitude G equal 29, where the Lyman alpha is expected to be detected with MOSAIC very easily. So this is something that MOSAIC will be able to do. And what you can see here on the right-hand side is just the expected signal to noise that you expect as a function of the continuum in the G band for the two observing modes of MOSAIC, the multi-IFU and the multiplex mode so just the individual fiber bundles on individual objects, you see that we obtain better signal to noise as a function of the magnitude for the multi-IFU. But of course, there is a price to pay. You only have 8 of them in the field of view, okay? And the reason for this is because you subtract a little bit better the sky contribution. But this has to be completely revisited, right? Because it was just a set of simulations done with a very early version of MOSAIC. Same thing here. You have, for instance, this very nice paper, Labé et al., showing these 6 galaxies at a redshift between 7 and 9, showing this very nice spectral distribution. And you want to really observe them to see if Lyman alpha appears there, and if possible, detect the UV continuum. Okay, so this is something that MOSAIC will be able to do in perfect synergy with JWST, with these 2 modes. Something that you can also add, I have to speed up a little bit, is of course to observe the Lyman alpha emission itself. The resolution of MOSAIC will be enough to catch the shape of the Lyman alpha line. So this will be also very, very useful, and of course to study all these different aspects I mentioned before, the prevalence of Lyman alpha emitters among Lyman breaks, the IgM by using the Lyman alpha profile, the global properties of this population, because you will have a spectroscopic measurement. Very nice and very important is to start to constrain the topology of the reionization with observations, for instance, by observing Lyman alpha over densities, because you have the multi-object capability, the Lyman alpha profiles of these guys in the over densities. For instance, I'm showing here one protocluster candidate at redshift about 7.7 behind a lensing cluster, so it is an extra push, okay, with a spectroscopic confirmation here for the red guys, still missing for the green ones. So you see that MOSAIC will be able to do this thing, observing these guys and determining the redshift and also studying the properties in the UV res frame. So this is what I'm saying here. And last slide for this topic. Something that is very interesting based on this multi-IFU is that you will be able to map the Lyman alpha emission, the extended Lyman alpha emission. We know today that this Lyman alpha emission very often, most of the cases, appears to be extended with respect to the stellar component. With a small mini IFU, you can catch this emission completely and then estimate, for instance, by combining these observations with James Webb in the Balmer region to estimate directly the escape fraction. Okay? Why not? But only with this kind of approach you can do it. So MOSAIC will be quite unique in this for detect the faint emission lines, in particular spatially resolved, as I said, carbon-4, helium-2, etc., etc. Don't forget the population 3 signatures like helium-2, 1640, that will be also possible to observe in these very high redshift galaxies. And of course, all the UV absorption lines that will be extremely useful for studying the physical properties of these galaxies. So I don't know if you are convinced, but if MOSAIC did not exist, we will have to invent it to do that. Okay, let's move a little bit faster now. This is about the science case number 2 that is closely related to science case number 3. Okay, so the 2 of them are really closely correlated. Here we want to answer to all these questions I'm going to repeat about the inventory of matter in the universe at high redshift by constraining structure formation. So here we are addressing different big questions about the distribution of gas, dark matter, and stars in galaxies at these very high redshifts by studying, for instance, the CGM over time regarding the gas, by studying the dark matter distribution with the rotational curves, for instance, of all these guys. We are going to see the intergalactic medium, how galaxies assemble their masses, by observing as well the cool gas between galaxies by tomography. Okay, so there are different cases here that are being explored with MOSAIC, starting with the rotational curves. This is the classical view that you all know. I'm not going to extend in the local universe, these flat rotational curves that witness the presence of dark matter. In the high redshift universe, we have now some important measurements at redshift 1 and 2, okay, coming from the recent papers showing this particular shapes of the rotational curves, showing sometimes a not so flat rotational curve. So what we want to do with MOSAIC is to address this question in a more general way by using the multi-IFU to measure the rotational curves of a large number of galaxies at redshift between 2 and 4, so much far away from the current studies. And this is going to provide for the first time a study on the evolution of the dark matter content on the stellar versus halo mass and the formation efficiency, and also, of course, the evolution of the disk and halo angular momentum. Just to give you an idea, this is, again, a simulation. This gives you the size of the rotation curve that you can actually see with the current IFUs for a scene for MOSAIC. So you see that a large part of the rotational curve of a typical galaxy at redshift 4 could be perfectly observable with these mini IFUs. This is just to give some numbers here. We expect to observe of the order of 1,000 galaxies, a large sample of them in any case, in such a way that we can catch all this evolution in different mass ranges around redshift 4 to perform this kind of analysis in a statistical way. I'm not going to extend more on that unless you have any question. Something very interesting as well is that MOSAIC will be able to map the cold gas distribution in the universe by tomography. You all know the tomography that is done with QSOs. Here, MOSAIC will be able to do so with LBGs. Okay? For this, we expect to have, by degrading the spectral resolution here to 2000, in a few hours typically, you can trace the absorbance along the line of sight of galaxies, and you can retrieve the distribution, three-dimensional distribution of this cold gas. Here you have a simulation to convince yourself. The reality, the original field is here at the bottom, and you see how well you reconstruct the field, depending on the signal to noise. This is for signal to noise of 10 or for 4, and you see that you are able to perfectly well identify this cosmic web in this way, but by using normal galaxies, I mean LBGs, right? Just because you are able to observe these absorbance. Of course, the general question we want to address in the Science Working Group 3, and not separated from the previous one, is to build up the dynamical properties of galaxies, spatially resolved properties of the interstellar medium in these distant galaxies, something that has never been done before, and also to associate these properties of the galaxies, the evolution of these properties with the environment, thanks to the multiplex capability. And this will be quite unique at redshift 4. For instance, just to illustrate my point, here is, again, a simulation showing how well you reconstruct the velocity field, the velocity dispersion, and the metallicity gradient of galaxies going down in mass, smaller and smaller masses, as compared to a galaxy at redshift 0 and the local universe. This is for galaxies at redshift 4, and you see that essentially you can still see something for masses below the typical M star. So there is no other way to do so unless you have a MOSAIC, okay, in an efficient way. So we expect for this to observe, again, large number of galaxies and combine all these different surveys together to address all these different big questions. Of course, there are here clear synergies with Harmony, Euclid, JWST, Rubin, Roman, etc., etc. This is my last slide regarding the science case. This is to say that there are many hot topics that are being addressed by the Science Working Group regarding different aspects of galaxy assembly and evolution that can be addressed only by MOSAIC using the combination of these three capabilities I have mentioned before. And these capabilities will allow us to analyze the properties of the resolved galaxies using the multi-IFU, for instance, to study protoclusters and build large-scale structure with the multiplex capability, of course, to study the stellar populations as well, and variations of the star formation history at different scales in a distant universe, again, for very small mass galaxies. And of course, some propositions as well to do some cosmology with H2 regions in the distant galaxies as well. This is a long, this has been a long question in the literature, and possibly MOSAIC could be the instrument to do this, to conduct this study at high redshift. I have one slide here to show, this is something that has to be updated for sure, just to compare the, let's say, the survey speed between MOSAIC and other facilities that possibly you know. For instance, this is for 500 objects that you want to observe. These are the numbers, typical numbers that I have shown before, so this is why 500 is not just like this. By comparing MOSAIC with the VLT moons and also with the TMT IRMS, and you see that for this, if you want to observe these 500 objects in good conditions with the same signal to noise, etc., MOSAIC will be about 4 times faster than moons, even if moons have a larger capability in terms of multiplex, and about 3 times faster than the TMT as well, thanks to a combination of both the resolution and the larger aperture. Of course, this has to be updated, so it's work in progress in the instrument performances. We expect to publish a red book with all this, the ensemble of all these topics I presented, typically at the end of phase B, so this should be for sure 2026, and the goal is to do it by the end of 2025. So if I summarize what I said, this is my last slide, about MOSAIC. I'm not going to read all these things. I have presented the characteristics of MOSAIC in terms of wavelength coverage, observing mode, and field of view, etc., and capabilities. MOSAIC is optimized for high survey speed, so this is something you have to take into account. And it will be, I hope so, your favorite redshift machine to follow up your favorite objects that you are observing with other facilities, okay? MOSAIC is absolutely needed for that. So if you want to integrate or know more about MOSAIC, please visit this place. It's very easy to Google it, and you will find it immediately. And I'm going to stop here. If you have questions, I am very sorry it was a little bit too long for the discussion, but please go ahead if you have questions or remarks. Thank you.